Welcome to lecture number 7 for ECE476, Advanced Embedded Systems. In this lecture, we're looking at serial I/O. So far, we've been using parallel I/O for our PIC board. What that means is each pin can drive one device or read one button. That works, but it uses up a lot of I/O pins. Plus, some of the I/O pins have other functions. For example, these pins are used for one serial port. This is the buzzer, the push buttons. These are the analog inputs. There just aren't that many I/O pins that aren't being used. Actually, these pins over here are used for the LCD display. So using a whole bunch of pins for push buttons is kind of a problem. Fortunately, there's a way around that. There's parallel I/O and serial I/O. What we've been doing so far is parallel I/O. Each pin reads one button or drives one LED. That's parallel. There's also serial I/O. That's what we'll be talking about in this lecture. With serial I/O, I can just have the Pi Pico, using just a few pins, drive a large number of devices. And it does that through a buffer, also known as a shift register. The trade-off is with parallel, I can control each device in one clock, or one instruction in Python. In serial I/O, it takes a bunch of clocks. I shift in the data one by one. After n shifts, I can then talk to n devices. So it's a little bit slower, but it uses fewer I/O pins. Now, in terms of serial communication, there's really two types. There's SPI and I2C. SPI came from Motorola. It's become an international standard, so is I2C. With SPI, you've got 4 wires, plus a common ground. I've got chip select, that tells the device when to start, when to stop the message. I've got a clock, I've got the data coming in, and the clock tells you when the data is valid. On the rising edge or falling edge, that's when you read the data. Plus I have the Pi Pico, that's the master talking to the slave, and the slave talking to the master. Now 3 of these pins can be shared, so I don't need 4 pins for every device. I need a separate chip select for each device though. So this device, if it's not being selected, it knows to ignore the serial port. If it is selected, it pays attention and latches in the data. That's SPI. I2C is another format. With I2C, you just have a 2-wire interface. Again, also works. Some devices use I2C. Some devices use SPI, and it kind of depends upon whatever the manufacturer chose. A lot of devices use both SPI and I2C. The Pi Pico supports both. In this lecture, we'll be looking at SPI, but there's also the I2C if you want. SPI is capable of 40 megabits per second. I2C is only 400 kilobits per second. So, starting out with SPI. With SPI, I've got the master, that would be the Pi Pico, talking to a large number of slave devices. Now, each slave, slide that over here, needs its own chip select, but I can share the clock, master out, and master in signals. One problem we have is that on any given bus, only one device can talk at a time. So that's not a problem on the master out. There's only one master is talking. On the master in, only one slave can be talking. That's part of what the chip select does. If that slave is selected, it's talking to the master. If it's not selected, it goes passive. The second point behind the chip select is if I have some data coming in, like this, ignoring the 2. If this is my data, where's the start, where's the end of the data? Well, if I just have the data being clocked in, I don't really know. That's the second function of chip select. If chip select does something like this, when it goes low, it's valid. This device knows that here's the data for me. Everything else ignore. So it kind of tells the slave when to start, when to end the message, what to deal with. In terms of the SPI format, there's 3 lines. there's chip select, your data lines, and clock lines. The one we'll be using, the chip select goes low to select the device, goes back high to turn it off. I'm shipping in data. This can either be most significant bit first or least significant bit first. We're doing most significant bit first. And the clock line, again, it can either be valid on the rising edge or falling edge. This is showing the data being valid on the rising edge of the clock. So, if I want to write to a serial device, I first need to pick one. So if we go to DigiKey and search for shift registers, there are, as of this recording, 2,214 shift registers I can pick from. These are shift registers where I write serial data and I get parallel data out. And I have the number of elements for each register, the number of bits. If I narrow the search to say what's in stock, what's active, meaning it's in production, 8 bits through hole, just because my breadboard is through hole, I'm down to 121 devices. If I narrow the search to parallel serial, this is I want to do serial in, or take a bunch of lines and read a bunch of lines using serial port. I get a manageable number. Picking one, kind of at random, is the 74HC165. If I select that one, I can pull up the data sheets. Now what that tells me is the voltage operation will work at 3.3 volts. That's good. It has a 13 nanosecond propagation delay time, plenty fast. Typically hardware is much, much faster than software. And it can drive 4 milliamps. So that should work. If you look at page 14 of the data sheet, it shows you how to connect it. So this would be the shift register right here. This would be the parallel data coming in. This is the serial data going to my PIC processor. And I can have multiple devices. Each one has its own chip select. That'd be the pin 9, the chip select. And then the serial data in and the clock. If we go further down, this kind of shows you what's inside. So this is going to your Pico chip. That's the serial data in. What I'm going to do is, first thing I do is I latch the data. That would be the load command. When I load it, all these latches load what's on the lines. So this is an inverter. So load goes down like this. That loads the data. Once I load it, I can then start shifting out the data. When I'm loaded, I see the value of H. If I pulse the clock, high and low, each data propagates down by 1. I'll then read G. Next clock, read F. Next clock, use E. So when I shift clock 8 times, that reads A through H. So that kind of tells you how to set up the hardware. I've got the data lines coming in, the load line, clock line, and output H. So H is going to go to my serial data input, GP12. The load line is your chip select, basically, and the clock line is the serial clock. So to read data, what I'm going to do is first pull the load line low. That loads the data. I will then pulse the clock high then low. On the low, the falling edge, that's when the data is valid. I will then read it. Pulse the clock again, read the next bit, and so on. After 16 reads, after 8 reads, I've got 1 latch. If I cascade 2 of them, after 16 clocks, I've got 16 values. So the beauty of serial ports is I can cascade as many as I want. Using just 3 lines, I can read as many binary inputs as I want. So in software, there's a couple ways of doing that. This is basically your program. When I pulse the clock line low, I know how to start reading the data. What I can do is come up with a subroutine called ECE476. When I call it, it's going to read in 8 bits of data and then return that. So what it does is, and this is just assuming 8 bits, so assuming I only have one of these connected. What the subroutine does is it first assumes latch was high, start with a clock low, wait 100 milliseconds, latch goes low, waits 100 milliseconds, then goes high. So there's your latch line. When I do that, I can start reading in the data. I'm going to bring the clock line high, wait for 100 milliseconds, shift in the data. So while the clock line is high, it's on this point right here, is where I read the data. I'll read the data, that's your binary input, read into X. Bring the clock line low, wait 100 milliseconds, and then repeat. Clock goes high, comes low. This is when I read the data, the next set of data. What the shift does is I'll read in the first data point, get shifted again, shift 8 times. So this assumes the most significant bit comes in first. And the last one I read will be the least significant bit. And you can do it either way. When I read in the data, I can either read it in by shifting left or shifting right. If I shift left, the first bit is the most significant bit. Shift right, the last bit is the most significant bit. That's kind of either way you do it. You kind of have to know which one you're doing, which one you want. It can be read either way. After 8 shifts, I return the value of X, and then the main routine is I just read the serial port. Every time I read it, I'm going to go through this process, latch in the data, shift in the data with 8 clocks, 8 shifts, return the 8-bit number. That's called bit banging. The nice thing about bit banging is you've got complete control over what happens. And I can use any I/O pin that I want. There are alternatives, however. Again, SPI is a very common de facto standard. So Python supports SPI. The Pi Pico supports SPI. Also supports I2C. So I can do the same thing using the features of the Pi Pico. If I import SPI from Python, I have access to the internal, or the hardware and the software versions of SPI. So if I define SPI, lowercase, to be SPI port number 1, I'm going to read the data at 1000 bits per second. Here's the polarity and phase, 0 and 0. Determine whether you're reading rising edge, falling edge, is the default high or default low. I'm going to read in 8 bits of data, and here are the I/O pins. This is the standard on the Pi Pico for serial port 1. There's also serial port 0. We're not using that one because that'll be used later on for the LCD display. Then to read the serial port, I just do SPI read. What the 2 does, says I want to read in 2 bytes of data. And the 42 is when I read, I can also write. I'm also going to write the number 42, the serial port, which we're not doing yet, but you could if you wanted. So using the SPI port, I can do the same thing. I'll take the latch, pull it low, then high. That latches the data. Now to read in 16 bits of data, I'll just do SPI read of 2. And what that'll do is that will clock in 16 bits of data, 2 bytes. And while I'm shifting in 16 bits of data, I'll also shift out the number 42, if you care. After read in 16 bits of data, I'll return that. So this is one way to read a bunch of binary inputs just using a couple I/O pins. So that's serial in. You can also look at serial output. Now, if I go to get DigiKey, again, there's a couple serial output pins, 74, 594, 595. They're both basically the same. 595 has an output enable, 594 doesn't. Pick a serial port that has serial in, parallel out. What that lets me do is it lets me write to a bunch of I/O pins using just 2-3 lines for the SPI port. Now if I look at the data sheets for the 594, this is what it looks like. Again, what it has, I've got the output, actually double output. This is a latch. When I shift in the data, the ones and zeros are going to keep on shifting. If this is driving valves, I don't want the valves to be open and closing as I shift in data. That's what the second part does. That's kind of a latch. When I'm done shifting in the data, I can take our clock, that's basically a latch, pulse the clock high then low. What that'll do is take whatever the shift register is holding, latch it, hold it, and then the output just changes at one time. So this is the latch output. And this is actually set up so a positive pulse latches the data. To shift in the data, this is your data line. And here is your clock line. It's set up so that the data is positive true. If I want to shift in 1, send a 1. I'll then take the clock line and pulse it. It goes high, then low. That pulses in the data. Send the next bit, pulse it, next bit, pulse it. In terms of the order, if this is the least significant bit, bottom is the most significant bit. When I shift in the data, I'll shift at most significant bit first. So that's kind of the idea. So this is the most significant bit. Here's the least significant bit. So in terms of timing, this is what I want the Pi Pico to do. When I want to send data, I'll take the clock line, and on the rising edge, I'll shift in the data, or shift out the data. The data line holds its value, again valid on the rising edge. After 8 shifts, I'll pulse the clock line at the latch line high and then low. That latches the data. So to write that in code, well, in terms of hardware, I just have 3 I/O pins. This is the data line. Here's the clock line. So this is the latch line. Here's the clock line. Let's see. That's for one device. I can cascade them. The most significant bit goes to the next shift register. Share the latch line, share the clock line, and go as many as you want. If I have 2 of them, I'll shift out 16 bits of data, 3 of them, 24 bits of data, and so on. Now to get this to work in software, here's what I do. I can again use bit banging or SPI. In terms of bit banging, I want to go through that same procedure. So I'm going to start with the latch. This is the latch starts out at 0. And when I'm done, I pulse the latch high then low. That locks in the data. In terms of the data coming in, start with the clock line high. So here's clock. It starts out high. I will then take the most significant bit. If it is a 1, output a 1, otherwise output a 0. So here's your data line. Sends out bit 7, most significant bit. Clock goes low. It's a millisecond, clock goes high. So here's bit number 7. I then do bit number 6. Send out bit number 6. Clock goes low, then high, output bit number 5. Repeat 8 times. When I'm done, latch goes high then low, saves the data. So let's try it. Here I'm just counting on X, setting that the 594. What that looks like is over here, I've got the 594. Here's bit number 1 or 0, 1, 2, 3. You can see it's counting in binary. On the oscilloscope, a kind of common theme in this class is oscilloscopes are your friend. Oscilloscopes make life a whole lot easier. You can actually see what's happening on the oscilloscope. So the clock line is in yellow, the data line is in blue. You can see as I'm counting, I can see the different bits. Again, it's the falling edge where the data is valid, which is what I wanted. In terms of looking at the output, oops, come back. There's my LEDs over here. I can see that I'm clocking the data correctly. It is counting. That's using bit banging. In terms of execution time, I can see how long it takes to send data. So I'm going to record the time before I send data, record the time afterwards, print the data that I sent out, and the time. This takes about 19 milliseconds to send 1 byte using bit banging. If I go to the SPI port, here's data coming out. I can also use the SPI port. In this case, I'm going to use SPI port 1. That's bits 10, 11, 12 for clock, master out, master in. The latch, I'm going to use pin 13. I actually changed that to pin 9 because pin 13 is the buzzer and it was getting annoying. Let's see. Okay, then I'll have the subroutine. I'll bring the latch low, ship out 16 bits of data, pulse the latch high then low. That reads the data, or sends out the data. I can try that in Thonny. Going over here, I change the baud rate to 3000 so it's easier to see on the oscilloscope. Polarity 0, phase 1. What that does for you, spread this out. This is polarity 0, phase 1. I want the data to be valid on the falling edge, and that's what I'm seeing. What the phase does, if I change that, let's do phase 0, rerun it. Now the data is valid on the rising edge. So that's what phase does. Do I want the data to be valid on the rising edge or falling edge? We want the data to be valid on the falling edge. What polarity does is, this is polarity 0. The line's idle low. If I change the polarity, now the clock line idles high. So, what is the default for clock, high or low? I'm going to use low. The ASDA test is the count. If you look at the count over here, is it counting? You can see that yes, it is. Here's my binary count. What the baud rate does is this tells you how fast you're shipping out the data. I'm currently using 3,000 bits per second. If I try 30,000 bits per second, spread this out. See, it's still counting valid. Data is valid on the falling edge, and it is counting correctly. Change it to 300 kilobits per second, or 300K. Faster still, spread it out. This is pushing the limit of my oscilloscope. Now it's still working. See, the count is still working. If I go to 3 million clocks per second, I'm getting garbage. Part of the problem, I've got these long wires. They add capacitance. If you put this on a PCB, I could go to a higher clock frequency. The counting, you can also see, is not correct. So because of my hardware, I can't go to 3 million clocks per second. If I built this on a PCB with power plane, ground plane, I could. But this is about as high as I can go given my setup with all these long wires. You can see on the oscilloscope, my clock is kind of marginal at 300 kilobits per second. But this really simplifies the coding. I just have to do an SPI write. Once I get the polarity and phase correct, it sends out the data. The other option or advantage is this guy right here. This is how many microseconds it takes to do a serial write. It takes 215 microseconds to do a serial write using the SPI port. Go back to bit banging. It was 19,000 microseconds or 19 milliseconds. So using the serial port is about 100 times faster. This is one of the reasons the Raspberry Pis do not include ports. The microchip that we used in 376 had port A, port B, port C, port D, port E, the different ports. When I write to a port, I write to 8 bits. They don't do that with the Raspberry Pi. The reason being is that, again, one of the I/O pins have other functions. Doing parallel input like that really uses up a lot of pins. The Raspberry Pi is really designed for parallel or for serial I/O. If I use a bunch of 165s, I can read basically an unlimited number of binary inputs just using the data in, clock, and load line. If I use a bunch of 595s, 594s, I can have basically an unlimited number of parallel outs just using 3 pins, data out, latch, and clock. And in this way, just using up 5 pins, I basically have unlimited number of inputs, unlimited number of binary outputs. That's really what the Raspberry Pi is designed for. So, kind of a sidelight, some fun things you can do with serial outputs. So this is an 8x8x8 LED cube. I can control the LEDs individually using a microprocessor like a Pico and get all sorts of pretty patterns. If you want to buy an 8x8x8 LED cube, you can get those on eBay. So here's a bunch you can get for like 28 bucks. It's a kit that you can buy. What it does is, using a microprocessor, I can control all 256 LEDs. And you might think that's a problem. How do you control 256 LEDs just using a microprocessor that only has 30 I/O pins? Well, it does it using the serial port. One of the fun things is an 8x8x8 LED cube. There are 256 LEDs in this cube. That is far more I/O pins than you have on a Raspberry Pi. So this is one where I cannot use parallel output to control each LED individually, but I can use serial outputs and control all 256 LEDs with just 11 outputs. So here's kind of the way the LED cubes work. I'm going to start with a 4x4x4 cube to kind of give you an idea. If I just take one slice of a 4x4x4 cube, here's your 4x4 array. I'd have 4 of these stacked side by side. If I just take one slice, I've got my 16 LEDs. Each column has the same anode sorted together. The cathodes are then shorted across. So what happens is, if I apply, I need a resistor right here, add a resistor and apply voltage, like 3.3 volts here, tie this to ground, all these LEDs turn on. Well, if all tied to ground, they'll turn on. If only one of them is tied to ground, these are floating, then only this LED turns on. So what I can do is, in software, I ground one of these 3 pins that says, am I talking about level 4, level 3, level 2, level 1. If level 4 is grounded, these pins tell you which LED on level 4 turned on. They could all be turned on, some turned on, none turned on. I'll then come over here and ground pin 3. When this is grounded, I can then tell you which LED on the next row is turned on, and so on and so on. So that would be for one row. The next row is identical. Be over here. I short the levels together, and I can just use one wire. That's all I need to electrically short them. Oftentimes what they do is they short them in 2 different places, and that just adds structural strength to the LED cube. Once I do that, I use some shift registers. Now to get the different elements, each of these will be the output of a shift register. I've got 16 lines going up, 16 anodes. It's going to have 16 outputs of a shift register. That'll let me use 2 shift registers with 8 outputs. So this will tell me which of these, like if this guy's turned on, which LEDs on level 4 are turned on. To control which level I turn on, I use the BJT transistor. The shift register controls the base. If this is turned on, this shorts the level to the ground. If it's 0 volts, it leaves it floating. Then what happens in software is I'll turn on the rows sequentially, turn on level 4, specify which LEDs are turned on level 4. Then I'll turn on level 3, specifies which LEDs are turned on level 3, 2, then 1. So each LED is actually flashing. The LED will be on for 25% of the time when it's on, because I'm scanning row 4, row 3, row 2, row 1, repeat. But that way I've got complete control over the LED array. I can turn on any LED that I want at 25% duty cycle, controlled by, there's 16 plus 4, 20 outputs, which is from 3 shift registers. That's kind of what the software then does. It just says I'm going to scan row 4, which LEDs, row 3, which LEDs, row 2, which LEDs, row 1, which LEDs, repeat. Keep on scanning the rows, have a slight delay, so I can see how long the LED is on, see some visual brightness. Then what you're going to see is when the LED is on, if I wait 2 milliseconds, I'm going to get this pattern for the LED. It's on for 2 milliseconds, off for 6, for a 25% duty cycle. That's a 4x4x4 LED array. Repeat the same pattern for an 8x8x8. The only difference is instead of being on 25% of the time, because there's 4 levels, I'll be on 12% of the time because there's 8 levels. Instead of using 16 verticals, I'll need 64 verticals. 64 verticals is 8 shift registers at 8 bits each. Plus I've got 8 levels. I'll have another shift register to say which level I'm turning on. The net result is 72 I/O pins or 9 shift registers. And with that, I'm controlling 256 LEDs using just 3 pins from the Pi Pico. And with that, you can output all sorts of different patterns. If you go to YouTube, there's lots of pretty LED 8x8x8 cube patterns you can output. That's one of the things you can do with serial outputs. I can control a large number of devices just using a few pins on your Pi Pico. So, in summary, parallel I/O, what we've been doing so far, it does work. It's really good if you're just grabbing a few things. However, it chews up a lot of I/O pins. Serial I/O really opens up possibilities with what you can do. If I use the SPI interface, I only need to use 3 or 4 wires to control a large number of devices. For example, I can control an 8x8x8 LED cube. By driving the SPI port, I can do that by using bit banging, just write the routines by hand. That's a little bit slow. Or just use the built-in features and the Pi Pico. The latter is like 100 times faster. So that is lecture number 7 for ECE476.